All right, guys, today we're on lesson 12.2, and we're going to start with task 1. So we are comparing exponential functions. Representations of exponential functions. Exponential functions can be expressed with a verbal description, an equation, a table, or a graph. The use of each representation has advantages and disadvantages. Example 1. Humans start as a single cell that divides into two new cells. Each of these cells divides into two new cells, and the cell division continues in this way, following an exponential pattern. The time it takes for the cell division to occur depends on many factors, including what kind of cells they are. All right, so it's showing an example of a cell, and it says it takes 1 day for this cell to divide. Okay, so you can see that the one cell divided into 2, and then 4, and then 8, and so on. So it says let T represent time in days, and P represent the population of the total number of cells. The exponential relationship can be represented in different ways, as shown in the following equation, table, and graph. All right, so here they're giving it to you in a verbal description. And then we're going to look at it as an equation. So one cell divides in takes 1 day to divide into two cells. So our base is going to be 2 raised to some power. All right, so if you take the table, you can take values for t or x. Normally it's x, but we're using t for time. And we're going to say 0, 1, 2, 3, etc. Okay, so this is the number of days that we're going to evaluate this function for. Remember, anything to the 0 power is 1, 2 to the first power is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth, 16, and so on. All right, if we graph these as ordered pairs, okay, so you've got t is on your x-axis and p of t is on your y-axis. So we can graph these as ordered pairs, and these are just the ordered pairs from the table above. So you can see that this is an exponential growth. Anything that curves up and gets faster as it goes, that is an example of exponential growth. All right, so it says compare the statements describing the initial value of the cell population and how it can be identified from the equation, the table, and the graph. So the initial value of the cell population is 1. We started with 1 cell, okay, because P of 0 equals 0, or 2 to the 0 power equals 1. Okay, so anything to the 0 power equals 1. Again, that's properties of exponents. Use the table entry to find the initial value. So if you look at the table value, the initial value is at 0, 1. And it says use the y-intercept of the graph to find the initial value. So, okay, so the y-intercept, remember, 0, 1, this would be your y-intercept. That would be your initial value. So it's not your x, but your y-intercept is always your initial value. All right, which statements about the domain and range of P are true? All right, so you got to remember that domain and range, a lot of times we'll say it's all real numbers, but this is a specific case. This is a real situation. So if you look up here, we're talking about division of cells, okay? So we don't have a negative number of cells. The smallest number we have is 0, and then we're taking just whole numbers, basically. There's no fractions. So we're looking at time in days, and that would be our domain. So our domain is time in days. So the domain is a set of all non-negative real numbers. The domain is a set of all whole numbers. So we're going to say whole numbers. The only difference between non-negative and whole numbers would be this one doesn't include 0. So we're going to include 0 because you can say 0 days. And the domain is a set of all real numbers. Normally that would be the case, but we're talking about cell division, so that doesn't work in this case. All right, now it says the range is a set of All right, your range is your y value, so 1, 2, 4, 8, etc. That is your range. So it means it's not going to be these two. And then it says the range is shown in the first column of the table and the t-coordinates of the points of the graph. So the range is in the second column. Remember, the domain is your t. Range is your p of t. So this one says the domain is shown in the first column. That's true. And as the t-coordinate of the points. All right, which statements about p are true? Select all that apply. All right, whether the function is increasing or decreasing is determined by the exponent. Okay, so it's not determined by the exponent. Remember, it's determined by the base. So whether the function is increasing or decreasing is determined by the base of the equation. So remember, in past lessons, if the base is greater than 1, 2 is greater than 1, then it's exponential growth. If the base is between 0 and 1, it's exponential decay. So the base determines whether it's increasing or decreasing. The table shows that P of t increases as time increases, so the function is increasing. That is true as well, because if you look at the table, P of t does increase. These numbers are getting larger as these numbers get larger. So that is a true statement as well. And then it says the table shows the right column is greater than the left column. So the function is increasing. That's not true. The left column is actually greater. So this one says the graph goes up to the right. So the function is increasing. Okay, so the graph goes up to the right. So the function is increasing. That is true. All right, which statement about the growth factor of the cell population are true? Select all that apply. The growth factor of the cell population is 1. Okay, it's not really a growth factor if it's 1, so it would just be 1 if it's 1. But it says the growth factor of the cell population is 2. That is true because your base was 2. So if you go back up here and look again at the equation, the base is 2, so that's your growth factor. All right, the growth factor is the base of the equation. That is also true. And the growth factor is the exponent of the equation. That's not true. It's not the exponent. The growth factor is the common ratio between the sequential values of P of t in the table or graph. The growth factor is the common ratio between the sequential values of t. All right, so it is the growth factor of P of t. So if you look above, you'll see that the growth factor is affecting this. So it's going 2, 4, 8. The growth factor is affecting the P of t, or your y value. All right, so that is all for task 1. If you have any questions, please let me know. Lesson 12.2, task 2. Compare growth and decay rates. Some people collect baseball cards to remember their favorite players. Other people trade and collect baseball cards as investments based on the value of the cards. All right, so the value of a card's growth. The value of a card grows exponentially and can be modeled by V of t equals A times 1 plus R to the t power. So remember, this is our exponential function. A baseball card is taken in two different appraisers. They both project that the value will grow exponentially. One projection is given in a table while the second projection is given in a graph. Which projection has the higher growth rate? All right, so projection 1 gives us the ordered pairs. You can see at year 0, the value is 300, so that's the initial value here. Year 1, it's 390, 2507, etc. All right, projection 2 has an initial value of 400 because 0, 400 is your y-intercept. That's your initial value. And then it looks like after 2 years, it's 576. All right, so let's compare the two. Projection 1 has an initial value for 300. So V of t equals 300 times 1 plus r to the t power. Why is a equal to 300? Choose the phrase to correctly complete the statement. All right, the initial value is 300, so that's why a is 300. All right, so it says V of 1 equals 300, so they're letting x be 1 and y be 390. So that just came from your table. See, year 1 goes with 390. So they're plugging in a point to find the interest rate. So we know A is 300, and we're using X and a Y to plug in to find our R value. All right, so which input-output pair is substituted into the equation? So we used 1 and 390. And that was just the next ordered pair in the table. All right, now if you solve this equation, okay, if you solve this equation, then you're going to see that the interest rate is 30%. All right, projection 2, the initial value of the baseball card is 400. All right, if you look back at the table, you will, not the table, the graph, you will see that 0, 400 is the initial value. Okay, that's your y-intercept. And it says, how can you identify the initial value from the graph? So it's going to be the y-intercept. And then if you choose the second point, which is given, this only gives you 2 points on the graph. It gives you a second point at 2, 576. So they're going to take the 2 and the 576. You can see they took the t and replaced it with 2. And they put the v of t as 576. So again, they're going to solve this for r, and you get 20%. So the table was 30%, the graph was 20%. So that means the first projection is going to yield a higher growth. All right, so it says, why is the positive square root the only root used in the solution? Well, remember, a negative square root in this case is not going to be a valid solution, because you're not going to have a negative number when you're talking about the value of a baseball card or a real life situation for that matter. All right, so it says the first projection has a higher growth rate. How does the growth rate affect the value of the baseball card? Well, the higher the growth rate, the quicker it's going to grow. So when it's exponential, that means it's going to grow even faster. And that's all for task 2. If you have any questions, please let me know.